Let's take a look at the next objective where we're going to calculate and interpret probabilities involving binomial random variables. So a binomial random variable is the count x of successes in a binomial setting. So it's just like a random variable. We have x represents a random variable, and we're going to count how many successes there are of this random variable x. So there's two important things to know about a binomial distribution. It's the probability distribution of x. Any binomial distribution is completely specified by two numbers: n, the number of trials of a chance process, and p, the probability of success for each trial. Those are the two things that we need to know once we've determined it is a binomial setting. So this is the same scenario from before. Genetics say that children receive genes from each of their parents independently. Each child of a particular set of parents has a probability of 0.25 of having type O blood type. Suppose these parents have 5 children, and X represents the number of children with type O blood type. So we want to know what's the probability that exactly one of the 5 children has type O blood type. So what we need to think through here is how many different ways could exactly one child have type O blood type. So we want to know what's the probability that x equals 1. So you can see I wrote out the probability of this first outcome is 0.25 times 0.75 4 times for the 4 failures. And instead of writing all of these out, because you don't need to, I just want to write it out one time so you can at least see where I'm getting these values. So this is the last statement here: 4 failures, 0.75. And 1 success is the last one, 0.25. So since there are 5 different ways, that means I'm just going to multiply this probability times itself 5 times instead of adding it 5 times together. So that's where I got this 5 from. This 0.25 to the first power represents there's 1 success in each of these 5 times. Then 0.75 represents there were 4 failures in each of these outcomes. So instead of adding this together 5 different times, I can just multiply it by 5 to get my probability of 0.3955. And so the probability of exactly one of the 5 children having type O blood type is 0.3955. So now let's take a look and see what's the probability that exactly 2 of the 5 children have type O blood type. So now what I'm going to do is I'm going to write out all the different ways I could have exactly 2 that have type O blood type. So the probability of exactly 2 having type O blood type is, it could be the first 2 and then the remaining 3 do not, or it could be the first and the third and every other one does not, or it could be the first and the fourth and every other one does not. I've written out all possible ways that there could be exactly 2 successes in 5 trials. So there are 10 different ways that there could be 2 children with type O blood type, or exactly 2. So in the previous problem, there were 5 different ways. In this problem, there are now going to be 10 different ways. And the probability of a success is still going to be 0.25, and the probability of a failure is still going to be 0.75. But now I have 2 successes in each of them. So I'm going to have 0.25 squared, and I have 3 failures. So that means I'm going to have 0.75 to the 3rd power. And then I'm going to have 10 different ways, so I'll be multiplying by 10 instead of 5. So you can see probability of there being exactly 2. There are 10 different ways times there were 2 successes, so that's why 0.25 is to the 2nd power, and 3 failures, so that's why 0.75 is to the 3rd power. So the probability of having exactly 2 is 0.2637. So there is a formula that you can use. You will never have to actually write out all of the different ways. I'm going to teach you a way to calculate all the different arrangements of the number of successes that you have using what's called the binomial coefficient. So the binomial coefficient for this problem was 5. The binomial coefficient for this problem was 10. And I'm going to show you how to calculate that value based on the number of trials and the number of successes in those trials. So here's the formula that we just used. We have the probability of x equaling some number. So in this case, we had x equals 2. So this k would be 2. K is the number of successes. The binomial coefficient is shown by n over k. That is the number of arrangements of successes based on the number of trials. P represents the probability of success. So for this problem, probability of success is 0.25, raised to k, which is the number of successes, 2 successes, and 1 minus p is the probability of a failure. And we wanted to have 3 failures with the 2 successes. So number of trials, 5 minus number of successes, which was 2. That's why we got 3 here. So this is the formula that we were using, but I wanted to show you why it looks the way it does. So let me write out a couple notes about this formula real quick. So again, this value here is the number of arrangements of successes. We had 5 or 10, but it's also called the binomial coefficient. P is the probability of a success. 1 minus P is the probability of a failure. K represents the number of successes that you want to find. So one thing to take a note of is if there's 5 trials, then the exponents will have to add up to 5. So you can see 2 successes, 3 failures, or 1 success and 4 failures. The exponents will have to add up to whatever the set number of trials is. So there are 2 different ways you can find what the binomial coefficient is, or the number of arrangements of successes. The first one is by hand, which I'm not going to have you do, but I want you to know how to do it at least so it's not foreign to you if you come across it. So the binomial coefficient, we read this as n choose k, and it's not division, it's not multiplication. This is just the symbol that is used to represent n choose k successes. So n is the number of trials, k is the number of successes. So n choose k, you have n factorial divided by k factorial times n minus k factorial. And factorial, so like 3 factorial would be 3 times 2 times 1. 10 factorial would be 10 times 9 times 8 times 7 times all the way down to 1. So the way you can find the number of successes for the set number of trials is to do this formula here. So let's go ahead and do this. Calculate binomial coefficient for probability of x equaling 3 by hand. And then I'll show you how to do it by the calculator as well. So we're going to do 5 choose 3. So we have n, set number of trials is 5 for this problem. K, number of successes, was 3 because we want to do probability of x being 3. And then so 5 minus 3 gives us 2 factorial. So now I'm going to write out 5 times 4, 3, 2, 1, and then same on the bottom here. So you can see if I've written out the factorials, the 3 times 2 times 1 cancels with the denominator, and so I'm left with 5 times 4, which is 20, divided by 2 times 1, which is 10. So the binomial coefficient for x equaling 3 is 10. Now I'm going to open up my calculator and show you how to do this on your calculator as well. So to find the binomial coefficient on the calculator, first I'm going to hit the number of trials, which was 5. Then I'm going to hit math and go over to probability, and then find NCR. And then I'm going to enter the number of successes. So 5 choose 3. This is what I want it to look like. And it will do the factorials on its own and send me the answer as 10. So this will be the way I prefer you to do it. I don't want you to write out the actual factorials. This is much, much easier. So remember, on the calculator, you're going to hit 5. You have to hit 5 before you actually do NCR, and then you hit 3 and hit enter. A lot of people accidentally hit NCR first, and then they hit 5 and they get the wrong answer. You have to hit 5 before you go to the NCR and the math probability, and you get the same answer as 10.